At NOAA's Office of Oceanic and Atmospheric Research and the head of the National Ocean Service. Prior to joining NOAA, Dr. Spinrad served as a research director with the U.S. Navy. He's taught at 2 universities. He's directed a major national nonprofit organization. He presided over a private company and worked as a research scientist. He also developed the National Ocean Sciences Bowl for high school students. He served as the U.S. Permanent Representative to the United Nations Intergovernmental Oceanographic Commission and was a recipient of presidential rank awards from Presidents George W. Bush and Barack Obama. And I can keep on going because he's a very distinguished man and he has a lot of credentials. But I'll just share with you that he got his BA in Earth and Planetary Sciences from the Johns Hopkins University in Baltimore, and his MS and PhD, both in oceanography, from that other OSU, Oregon State University. So we're really honored to have Dr. Spinrad with us today.
Thank you, Shelley. I'm going to set this here. Can I set this mic up on the stand here? It'll pick me up okay? Take care of all the AV. I think I probably ought to start by asking everybody to applaud the OSU tech folks who got everything set for the feed from DC. Well done. Nice job. That oftentimes is a real challenge. Let me also thank Shelley for that kind invitation and for sponsoring this and providing us some lunches. I appreciate all of the great effort of the American Lung Association. And also let me thank Ellen for the hospitality here at the Bird, Polar, and Climate Research Center. It's a real treat to be here at the OSU. I got that part right. I also, from a personal standpoint, want to convey to everyone here the greetings and regrets from my boss, Dr. Catherine Sullivan, the NOAA administrator. Many of you know Kathy from her work here in Columbus with COSI and with the university, and she really regrets she could not be here today, but I'll try to fill in as best as I can. And maybe the best thing for me to do in starting is to just get a sense of the audience, and I'm just curious, by a show of hands, how many health professionals do we have in the audience? And use a broad definition. Okay, great, a handful. How many environmental scientists do we have here by a broad definition? So pretty good mix of both of those. And then I won't go through what everybody else is, but I'm going to target my comments for a broad perspective and try to complement what you just heard from the White House over the last couple of hours. And it's really about how intricately and intimately connected the issues of climate and human health really are. And if you think about it, so many of the human health issues have a tie to the climate issues of heat, flood, drought. When you look at vector-borne disease, zoonotic disease, how wildlife transmits disease, those have obvious connections to what's going on with climate and climate change. At the National Oceanic and Atmospheric Administration, we are a science-based service agency, and our currency of the realm, if you will, is a predictive capability. That is to take the information about the environment, arguably environmental intelligence, and translate that into how can we anticipate change in the environment? How can we predict what that change might be? How can we carry out some of the simulations, the what ifs? What if the following happens in the environment? How will that affect other parts of the environment? So, as you might imagine, a major goal for us at NOAA as an environmental intelligence agency is to try to understand the linkages between these environmental conditions and health outcomes. And I'm delighted by having the foundation, if you will, for what we heard over the last couple of hours, because you heard a number of different perspectives from John Holdren, the President's Science Advisor, from a somewhat sedate and calm Gina McCarthy, the head of the EPA, who obviously is very passionate about these issues and the impacts that they have. Let me talk a little bit about the role of environmental intelligence in the context of climate change. And I should probably start by saying what you're seeing is a demand for more of this kind of intelligence, a demand for more information, more tools, more products, more data. And the demands are increasing largely because we're seeing some significant changes. So many of you know that 2014 was the warmest year on record. 2015 is on track to surpass that record. If you were paying attention, you noticed that there's triple-digit temperatures back in DC. It's rather warm here in Columbus, I might add, as well. And this is a trend that we're going to be seeing more of. We're seeing more frequent and intense weather, significant weather events, billion-dollar disasters. Last year, for example, we had 8 multi-billion-dollar disasters, natural disasters. And remember, last year was one where we didn't have significant landfalling named hurricanes, and that oftentimes is a major contributor to those numbers of significant weather events. Multiple stressors are affecting natural systems on all fronts and intensifying. So we need resources. So one example of the kind of resource that we've got is the National Climate Assessment that came out last year, and many of you have a lot of familiarity with that. Many of you may have even, in fact, contributed to that National Climate Assessment. And that assessment provides the conclusive evidence of the human-induced climate change and its continuing strengthening as time passes. And also some of the impacts are strengthening. And so, for example, we're seeing such effects as rising sea levels, including more instances of nuisance flooding. If you talk to friends of yours in Norfolk, Hampton Roads, people who work for the Navy in that part of the country will tell you there are severe consequences to king tides, they're sometimes called, but this nuisance flooding that's becoming more and more frequent. More areas are affected by wildfires out west. As you heard, I still have a faculty appointment at the other OSU. And in fact, I have a home up in the Cascade Mountains in Bend, Oregon, where last year we had significant fires. In fact, fires that came so close to my property, we actually had to start bringing out the hoses and hosing down the roof. So we're all starting to feel some of these kinds of effects. We're seeing shorter and warmer winters across the country and longer and hotter summers. Strong droughts in places like the Southwest, but when you look at the tens of millions of people that are impacted by these droughts, it's not exclusively a Southern California effect. It's something that's hitting the whole country. And then you saw by the same token what happened down in Texas just last month with these almost biblical floods, significant flooding events. So consequently, you have to start asking, what are the impacts? What are the downstream predicted understandings about the consequences for health? And what are our improvements in both the ability to forecast and predict these phenomena and yield better value for the public health community and the public at large? Here in Ohio, probably the best example I can cite is what happens with Lake Erie with the harmful algal bloom every year. And this is a phenomenon that's plagued so much of the community for quite a few years. In fact, last year in 2014, there was a 2-day ban on drinking water, and this event left nearly 400,000 people in Ohio without drinking water for that period of time. So what do you do about it? Well, one of the things we realized is that we now start to have understanding of the parameters that can be used to predict the onset and the frequency, the magnitude of harmful algal blooms in an area like Lake Erie. So we have started to develop an operational forecast predictive capability for harmful algal blooms. And in fact, just last month, NOAA and some of our partners started to begin to issue a new experimental forecast system, an early season forecast. And if you're wondering, you can pull this up on the web. And right now, based on what we understand about river flows and availability of fresh water, it looks like the bloom that will come on the middle of this summer will not be as severe as last year, certainly not as severe as 2011 and 2013. To put it in broader context, we now have a standardized bloom severity index. For reference, the 2011 bloom was an index of 10, the maximum. Last year was about a 6, and the prediction this year is that it'll be somewhere between 2 and 4. And the uncertainty associated with that prediction reduces over time. So when we start putting out the weekly reports on the 1st of July, we should be able to get that uncertainty down to an even finer degree. We at NOAA are working with our colleagues at NASA, at EPA, U.S. Geological Survey, and just recently we announced a program of study, a research effort, to provide an even more improved early warning system using some of the color data coming from Earth imaging satellites. How much lead time do we need? What does the community want? How are we going to improve these harmful algal bloom forecasts? I'll say a little bit more about how you get that information. We can't do this in a cubby. We can't just sit in a cubby hole and say, let's think up a good way to develop a predictive system. There has to be an engagement. There has to be an engagement with the civil and local communities. There has to be an engagement with the public health community. We don't know what the required lead times are for the public health community. We have to have that dialogue. We don't know what the best lead time is for a forecast from the water management community. We have to engage in that dialogue, and there's an upcoming event in Chicago that should help us try to define that. So the administration has been undertaking a number of significant activities over the last couple of years and making some real progress with respect to providing improved products, providing a better understanding of what's needed, providing data for people to use for their own applications, tailored products, tailored services. Like I said, data are the currency of the realm. So of particular note, last March in 2014, we and NASA initiated the Climate Data Initiative, and this was one of the initiatives of the administration. And the idea here is to undertake an ambitious effort to bring the extensive data collections that the public sector has, that the federal government has, and make them available to just about anyone, the private, the philanthropic sectors that want to develop new products. Because that's part of this thinking, is that many of the products and services are going to be developed by third-party service providers, uniquely tailored products to meet particular needs. So it's been a major effort, and thus far, there are more than 135 health-related data sets on that Climate Data Initiative. And if you'd like to take a look, a lot of times it's cumbersome to access these issues on the web. So take out a pencil and paper, and I'll give you the website that you can go to. I've memorized it. You ready? It's data.gov. Okay? Go in there and you'll see a whole collection of data from the federal government, and there is one that's specifically tied to health. If you go to that site, you can pull down those 135 data sets and get a sense of the diversity and applicability of those. The next thing that the administration did was last May, we issued the third U.S. National Climate Assessment, which is unquestionably the most authoritative and comprehensive source of the scientific information about domestic impacts of climate change at a reasonably granular level, too. So it's one thing to look at global models, it's one thing to look at general predictions, it's another to say, what's going to happen in my county in Ohio? What's going to happen in my county in Texas? What are the changes that I might be able to start to see with respect to surface temperature, surface precipitation? Then the final product that I want to talk about briefly is the Climate Resilience Toolkit, which came out last November, which is a very useful set of products based on scenarios where you can go in and get some sense of what are the tools, where's the subject matter expertise? If I don't fully understand data with respect to changes in surface temperature over the decades, how do I learn more about what a global surface temperature record means? What do changes in precipitation mean? When I hear more frequent, more intense severe weather events, what exactly does that mean? And oh, by the way, what are the implications for the transportation sector, the energy sector, or the health sector? So take a look at the Climate Resilience Toolkit and you'll get another idea of some of the kinds of products that are rolling out. So it's important to bear in mind that climate change can really affect human health in two fundamental ways. The first is by changing the severity or the frequency of the health problems that are already affected by climate and weather factors. Harsher, more of the kinds of storms, the kinds of severe weather events we talked about. And the second is by creating some unprecedented or unanticipated health problems or health threats in places where they haven't previously occurred. And the classic example there is the migration of vectors for vector-borne disease as a result of the environment changing, whether it's Lyme disease from ticks or mosquitoes from changes in precipitation. So within NOAA, to that effect, we're continuing to try to push the frontiers of environmental health services, as I've just indicated. And we see this as having immediate and important impacts. With regard to heat, I talked a little bit about something like harmful algal blooms. Let's talk about something that's going to hit an even broader portion of the population. And following up on some of what you heard in the White House forum just in the last couple of hours, we know, for example, that between 1979 and 2003, excessive heat exposure caused 8,015 deaths, at least, in the US. And during that period, more people died from heat exposure, extreme heat, than died from hurricanes, tornadoes, floods, and earthquakes combined. This is a dramatic statistic. So the last national climate assessment that I alluded to found that extreme heat events will be even more frequent and more intense in the future. And so the way to look at this is that what now seems like an unusually hot day, such as what we're seeing back in DC right now, will become commonplace. Research from a variety of recent journals suggests that a warmer future is projected to lead to increases in future mortality on the order of thousands to tens of thousands of additional deaths per year in the US by the end of this century. Now, there is a document many of you have seen. A draft version was put out by the US Global Change Research Program. It's a report on climate and health assessment that is currently in review, should be released as a final report in the late fall this year. But a lot of those kinds of issues and statistics are going to come out, and they're going to be specific to the impact of increased weather events, drought, vector-borne disease, all of those different sectors, if you will. You just heard from Administrator McCarthy the really phenomenal finding from the EPA report that was just released yesterday that climate change in the U.S. The study is called Climate Change in the U.S. Benefits of Global Action, and basically it's a scenario exercise. So if we do reduce greenhouse gas emissions, as we have said we intend to do, by one estimate, by 2100, that will result in 57,000 fewer deaths due to poor air quality alone. That was the report she alluded to that said, look up your favorite subject and you'll find what the impacts are. So I encourage you to take a look at that EPA report. One product that we will be developing, and in fact the White House has just announced this today, so you're hearing some news breaking as it were, is the development of a national integrated heat health information system. A few years ago, we developed a national integrated drought information system at the behest of the Western Governors Association. They saw what was happening with respect to drought. They said, we need a place to go that represents the integration of all of the government, all of the public efforts for acquiring data, for developing predictive skill, for providing those translated scientific reports into understandable decision aids for local decision makers and policy makers. Well, we will be doing the same kind of thing with the National Integrated Heat Health Information System, only this time we'll be doing it in collaboration with CDC, for example. It's a new initiative. In the near term, we're working toward a website that summarizes the initiative itself and provides some links to resources across the government associated with heat health. And it'll be available for the public use in that early form later this summer. The plan is to have the fully integrated resource, fully operational as it were, for the 2016 heat season, so roughly a year from now. This National Integrated Heat Health Information System, in fact, it's so new, I'm not sure how we're supposed to pronounce the acronym, so I'm going to call it NIHIS for now. So NIHIS is a critical component of bringing some of this environmental intelligence that I alluded to bear on some community resilience. How do we make communities better prepared, give them the information? If you had timely, actionable, reliable information with regard to heat health, with regard to major heat events coming up, say, a week from now, 2 weeks from now, how might you respond? How might you pre-position if you work for FEMA or if you work for a state emergency management group? How might you pre-position resources, ice making, water, all of those things that are necessary for responding to a major heat event. Next month, at the end of July, there's going to be a workshop held in Chicago on the development of climate information systems for heat health early warning, assessing knowledge needs and the path forward. That's what I alluded to a few minutes ago, where I said, let's get all of the decision makers, public health experts, climate experts, environmental scientists together to talk about what are the needs. And we want to do this in a way that takes advantage of all of the best knowledge and understanding. So it's actually a global event, including the World Meteorological Organization and several other international partners, along with us at NOAA and the CDC. And the workshop, of course, is going to feed into the development of this NIHIS, the National Integrated Heat Health Information System. We're working right now to develop an operational product that does provide that 2-week outlook. If you think about that, that's a pretty high bar, the ability to provide that. But I remind you that in terms of weather forecasting, we are basically making a 24-hour improvement every 10 years. What does that mean? That means that the 72-hour forecast that you look at today is as accurate as the 48-hour forecast was 10 years ago. So think about that. How do you plan your day? How much trust do you have in the 24-hour forecast? I have a lot of trust in that. The 48, the 72, 96-hour forecast. Being able to provide a 2-week forecast on heat health events is a really important goal for us, but we're not stopping there, because it's clear from talking to stakeholders that there's value in extending this into the climate patterns that go into the 3 to 4 week excessive heat early warning information system. So that's our goal. So we're evolving these various heat products and services to provide more advanced warnings of higher accuracy, provide some decision support services that are going to enable protection of life and property. Unquestionably, they're going to enable it. They're going to protect, they're going to provide the kinds of mitigations against the kinds of numbers that you heard Administrator McCarthy allude to. And these activities are part of a broader ongoing effort to deliver useful information on current and emerging health risks and benefits. Remember, NOAA is a science-based service agency. And what you're seeing here is really good government. It's an agency whose responsibility it is to monitor the environment, to take measurements and develop predictive capabilities without a particular political agenda, and say, how can this serve the needs of each of these particular sectors, including, notably, the public health sector. So, in conclusion, I hope what I've been able to do is convey to you that while I'm here as a representative of the administration writ large, and I'm delighted to present the kind of things that we are doing, I'm emphasizing a lot of what we're doing at NOAA and how our efforts are an integral part of this administration's real dedication to developing and preparing the United States for the impacts of climate change. And we do this for ourselves, for our communities, for our friends, and probably mostly for our children. Thank you. So I'd be glad to take questions, and what we're going to do is pass the mic around for questions so we're adequately recording this, and I will do my best to try to translate the question back for the audience that's picking up on my mic here. Follow that? Got that? Okay, good. Have at me, please.
We have about 15 minutes for questions, so who would like to begin?
So in terms of getting bringing down or increasing the time forward for the forecasts, what would you say is the single, what is the greatest challenge in extending those forecasts, right? Is it some aspect of the climate science? Is it the computing capability? What are the grand challenges for NOAA to forecast further into the future?
So the question is, what are the challenges as we talk about extending the forecast? And I would broaden the question to include whether we're talking about weather forecasts or climate projections, if you're good with that. Yeah, okay. So what are the challenges in extending the forecast? Well, one of the key challenges is having the data. And I would argue that in the world of weather and climate, and I include in climate a whole range of additional environmental parameters, ocean observations, atmospheric observations. We don't have a lot of data. Our observational systems provide good data for forecasts for some standard products, but as we want to extend those, we need probably data with more resolution in time and space. And so one way we're going about that is trying to be creative in acquiring data. So there's a very active citizen science effort. And right now, for example, our ability to acquire surface temperature data, for example, is dramatically improved because there are temperature sensors all over the place. Every new car has a reasonably accurate temperature sensor, for example. How do we fold that into our temperature observation system? So part of it is getting the data. Part of it is, especially in the climate world, understanding the influences of various forcing factors, if you will. So the role of clouds is a classic example. That's probably one of the toughest variables to manage in terms of how clouds affect radiation and how radiation affects temperature. So what we tend to do is we tend to parameterize. We tend to say, well, let's assume the clouds are of this structure, magnitude, density in a particular square kilometer, and then we'll build it into the climate model. The better we can understand the physics associated with how clouds affect radiative forcing, the better off we're going to be able to extend those models. The third challenge, I would say, is in our abilities to assimilate the data. So we may have a perfect model. We may have a lot of data being collected all over the world or all over a particular area. How do you get those data into the model in a way that they are actually improving the model as you move along? So there's some sophisticated techniques for data assimilation that allow you to basically run your model a little bit, assimilate some data, run the model again to see if assimilating those data actually made it any better, and then send it forward with the assimilated data. But how you assimilate the data into the model is an area of study that's probably one of our biggest challenges.
One of the things that hasn't been directly addressed today as a public health effect of climate change is food scarcity. What does NOAA have, or does NOAA have any projects or projections related to our food supply system?
So the question is about food scarcity and more specifically, what's NOAA doing about it? So we tend to talk about food security in the sense that scarcity is a very relative term, and food security also starts to invoke water security, energy security, environmental security, if you will. So what we're doing, we don't have as an objective, if you will, agriculture or food security, with the exception that we manage the nation's marine fisheries, which is part of the food security. So for that part that we have direct management responsibility for the fisheries, which represents a significant portion of protein consumed by people, and incidentally, the projection is Americans will consume twice as much fish protein by the year 2025 as we currently do right now. And that could be through aquaculture and other mechanisms. So what we do directly is we manage sustainably the availability of those fisheries. We also have a responsibility for undertaking protections regarding illegal and unreported and unregulated fisheries around the world, because that ultimately leads to shortages of some of the fisheries. And we have research programs associated with developing aquaculture and mariculture programs. But I suspect your question was not so much about the fisheries side, because after all, most of the food security issues are tied to terrestrial agriculture. And so what we do is we try to provide the climate information and the projections that suggest if precipitation changes this way in this area, if heat changes this way in this area, we then turn this over to the agricultural experts and say, what does this do to crop species? What does this do to crop yields? That information is the foundational information upon which agronomists, agricultural scientists can say this is the projected change. Interestingly, for example, just yesterday in the Washington Post, there was a story about how many wineries in Quebec are now looking forward to projected changes, and they are looking at the models of changes in surface temperature and precipitation to determine what kinds of grapes to plant in Quebec. So from that standpoint, our job is less about addressing food security, food scarcity directly, and more providing the climate projections and predictions, but to do so in a way that you can meaningfully translate that to agricultural yield. So if the agricultural community says that soil moisture is probably the most significant parameter for crop X in the Midwest, we're going to focus our attention on providing the best predicted and projected capabilities for how soil moisture might change under a variety of different scenarios associated with climate change. Does that get to your question? Thank
you. Regarding short-lived climate forces, ozone, methane, black carbon, do you see practical policy implementation in the next 20 years that can impact the risk of global warming for this century?
So the question is about some of the shorter-lived radiative forcing stressors, if you will, such as ozone, methane, and black carbon, and how, I want to make sure I get it right, how changes or policy decisions now can affect the longer term for this century. I think probably the best way to start that is to say any changes are going to have some impact. And so consequently, we know what the relative radiative forcings are of each of these stressing factors, if you will, are. It's not a trade-off, as you well know. You can't simply say so many molecules of methane are going to offset so many molecules of carbon dioxide because of the duration in the atmosphere, the life in the atmosphere, if you will, of methane versus carbon dioxide. My own view is that what we need to do is provide the clear information about what adjustments to greenhouse gases and to things like black carbon soot will have on the atmosphere, and then make the decision about what policy is most appropriate for controls. Because the part that we don't deal with in my agency is the economic downstream consequences. So if we make a particular, if we run a particular scenario associated with changes to, let's just use methane as an easy example. We are not the agency, we're not in a position to say this is what the economic consequences are, these are the industrial impacts. We can, however, turn the knobs and dials on the atmospheric forcing to conclude what the physical changes to the atmosphere might be. I think any climate scientist will tell you that the most dramatic dial on that dashboard, if you will, is going to be carbon dioxide reduction and its associated long-term consequences with regard to greenhouse effects.
Preceding policy, man for some time has been nudging nature along and wondering if NOAA knows of or is involved in research that may be involved in using some of our technology to assist nature. I think of an example when I was about 10 years ago in Thailand, and during the hot season, and all of a sudden there was a cloud and we had rain, and they said, oh, that's the king's rain, that he had using some kind of seeding the clouds to get rain. Do we have anything of that nature going on in research potential now?
So the National Academy of Sciences just concluded a study, which they broke out into two studies on what's now called climate intervention. And it basically is looking at two aspects. One is in effect, carbon capture and sequestration, removal of carbon dioxide from not just the atmosphere, but the oceans, which serve as a major sink for carbon dioxide. And then the other is what sometimes is called solar radiation management, and that would be increasing the reflectance, affecting albedo, that sort of thing. And I think in a nutshell, and I encourage you to take a look at that, those two reports that came out of the National Research Council. It was back in January when the reports came out. And basically what those reports said was that the fundamental physics is reasonably well defined, but what we don't understand are the collateral consequences of trying to work any of those solutions. And so there are a number of well-defined research projects that would be needed, that would necessitate work. We'd need to do those kinds of activities before we could make any sort of conclusive decision with respect to the effectiveness of either of those kinds of approaches. And of course, in either of those categories, the solar radiation management, the carbon capture, there's an abundance of different approaches, everything from iron fertilization in the sea to actual mechanical withdrawal of carbon in the atmosphere. But the jury is out with respect to a definitive decision as to whether that can or cannot work in a long-term solution without knowing what the secondary and tertiary consequences of taking those actions might be.
All right, we have time for one more question.
I am curious as to whether NOAA has any projections on the impacts that Arctic oil drilling will have on the ecosystem.
So the question is, what projections do we have on the impacts of oil drilling in the Arctic? And as I think everybody knows, Shell Oil has been given approvals to do some exploratory drilling in the Arctic. And it's a very important question, especially in light of what we saw with Deepwater Horizon some 5 years ago. So our plans are to undertake the field experiments to try to develop the predictive capabilities. So even something as fundamental as do we have adequate oil spill trajectory models? The answer to that question is yes, but we do have standard models for that sort of thing. But the Arctic is a unique environment. How much do we know about the bathymetry? How much do we know about the impacts of sea ice on oil dispersion? How much do we know about the effects or capabilities of oil dispersants in that particular kind of water, for example? So we are undertaking a variety of different studies. One of the other things is there's, I would argue, a need to understand better what the whole ecosystem dynamics is in the Arctic. Right now, there are not major fisheries in the Arctic, commercial fisheries, but that doesn't mean there might not be in years to come. What is the ecosystem foundation right now, and how might it change under a variety of different conditions? And then for example, can we tease out the climate change impacts on those particular ecosystems and use that as a baseline for understanding what potential consequences of drilling might be in the Arctic? And then, of course, there are issues associated with things like acoustics, and how much do we know about the acoustic patterns and the behavior of the whole drilling activity on those particular systems and those specific fauna in that area, for example. So what I've succeeded in doing here is telling you, here are a variety of the unknowns. And so the assurance is that we're capturing all of those unknowns and trying to prioritize where to invest in understanding that better so that we can have the baseline of information around which drilling can occur. But the knowledge right now with respect to direct impacts is not as robust as it could be.
Okay.
Thank you very much.